A single crane, rated for 4,000 tons, once stopped America's newest nuclear power plant dead in its tracks, not by failure, but by a veteran's split-second call. In The 3 Biggest American Cranes on Earth, explained in 22 minutes, we'll uncover how machines built to defy physics faced disasters that threatened billions, and why what happened next changed industrial safety forever. What gave these giants their edge when every second risked catastrophe? At the heart of America's new generation of nuclear construction stands a machine that rewrites the rules of heavy lifting. The Big A-Frame Ring Derrick, or AFRD. Its purpose is clear from the numbers alone. Certified to lift 4,000 tons, the AFRD towers above the site with a 560-foot lattice boom, longer than the length of a city block and taller than most downtown skyscrapers. The boom itself is a web of high-strength steel, engineered for both reach and resilience, designed to swing loads that would overwhelm any ordinary crane. What truly sets the AFRD apart is the ring it rides on, a 280-foot diameter steel track, forming a perfect circle embedded in the ground. This ring allows the entire crane to rotate a full 360 degrees, covering an area of 28 acres from a single fixed position. In practical terms, that means the crane can reach any corner of a nuclear plant site without ever needing to be moved, a feat that saves weeks of downtime and millions in transport costs. The secret to this stability lies beneath the surface. Over 5,000 tons of concrete ballast anchor the ring, forming a massive counterweight system that resists not just the pull of gravity, but the unpredictable forces of wind and weather. Every lift is a balance between the enormous weight on the hook and the silent strength of the ground below. When the AFRD swings a 1,500-ton reactor module out to a 440-foot radius, the forces at play rival those of a small earthquake. The lattice boom, built from modular sections, can be configured for the precise demands of each lift. Engineers assemble the boom piece by piece, adjusting length and angle to handle everything from containment vessel domes to turbine rotors. The ring track itself is laid out with millimeter precision, surveyed and checked before the first load ever leaves the ground. Every component of the AFRD is purpose-built for the nuclear industry's unique demands. Modular construction methods mean entire reactor buildings arrive at the site in sections weighing thousands of tons, ready to be swung into place in a single, decisive move. The ring-based design allows crews to set these modules with pinpoint accuracy, eliminating the need for multiple smaller cranes and reducing the risk of error. But with power and reach come new challenges. The same features that give the AFRD its edge: enormous coverage, massive counterweights, and a boom that soars above the site also make it sensitive to the elements. Even a moderate wind can turn a suspended module into a giant sail, threatening the delicate balance between hook and ballast. Every lift is planned with weather in mind, and the tension between schedule and safety is ever present. Before any drama unfolds, the technical reality is unyielding. The AFRD's engineering is both its strength and its test. When the clouds gather and the wind rises, everything depends on the machine's design and the judgment of those who control it. At Vogtle Nuclear Plant, a gray front pressed in from the southeast, stirring the flags above the site and rattling the chain-link fence. On the main deck, the big AFRD loomed, rigged for a 3,740-ton reactor module pick, one of the heaviest ever attempted in American nuclear construction. In the operator's cab, a veteran in his late 60s scanned the digital wind gauge. The needle hovered at 22 miles per hour, climbing in fitful bursts. On the radio, site management pressed for the go-ahead. Schedules were tight, and every lost hour meant cost overruns. But the operator's hands stayed steady on the controls. He'd worked Derrick since the days when lifts were calculated on paper and wind was judged by the feel of a flag, not a sensor. The lift director called out the numbers: 25 miles per hour sustained, gusts higher. Protocol for a superlift called for a hard stop at that threshold. The module, nearly 80 feet tall, would act as a sail in the wind, amplifying every gust into a force that could unbalance even the AFRD's 5,000-ton counterweight buried in the Georgia clay. The operator keyed the mic, voice calm. "Parking the hook, 4-hour hold." The crew grumbled, some anxious about the mounting delay. But on the ground, union stewards and old hands nodded. In nuclear work, safety always outranks speed. The operator's judgment, earned over decades, carried more weight than any project manager's spreadsheet. He watched the clouds roll in, listening to the wind batter the cab. The site fell quiet. No movement, just the low hum of the weather monitor and the distant rumble of thunder. As the storm peaked, gusts hit 28 miles per hour. The module rocked gently in its cradle, still earthbound, while the AFRD's boom swayed above the silent site. The operator sipped his coffee, unfazed by the tension. "I'd rather take a ribbing about delays," he later told a safety officer, "than see anyone get hurt." 4 hours later, the wind dropped below 20 miles per hour. The all-clear came. The operator ran through the checklist again, eyes on each dial, ears tuned to the subtle creaks of the rigging. Only when every measure checked out did he edge the controls forward, lifting the module clear and swinging it into place with the precision of a practiced hand. The lift was completed without incident, and the crew returned to work, ribbing the operator for his caution, but quietly grateful for it. That day's decision didn't just avoid disaster, it changed how future jobs would be run. The pause and its reasoning were written up in Big's safety bulletins, prompting a review of wind monitoring and the adoption of autonomous weather sensors for all superlifts. Across the industry, the story spread, proof that even the most advanced machines still depend on the judgment of the person in the seat, weighing risk against pressure and choosing safety every time. The Manitowoc 31,000 stands apart from traditional crawler cranes thanks to a breakthrough in counterweight engineering. At its core is the Variable Position Counterweight, or VPC, a system that doesn't just balance the crane, it actively thinks ahead. Instead of relying on a fixed stack of counterweights at the rear, the 31,000's VPC shifts a massive 3.5 million pound ballast pack along tracks, moving it anywhere from 8 to 29 meters behind the boom. This isn't just clever, it's transformative. The counterweight glides automatically, guided by sensors and algorithms that respond in real time as the boom swings or the load changes position. On a crowded job site, that mobility is everything. Where older cranes would need acres of reinforced ground to handle their static counterweights, the 31,000 cuts that requirement in half. Crews can assemble the crane on tighter footprints, even weaving it into stadium construction or refinery upgrades where every square foot is precious. The VPC's flexibility means less time spent laying down steel mats or pouring temporary foundations. That translates to faster setup, lower costs, and fewer disruptions, advantages that don't just look good on paper, but are felt in the daily rhythm of the project. During a major stadium build, the 31,000's crawler base allowed it to maneuver between partially finished seating bowls and under the looming skeleton of the roof. With a rated capacity of 2,535 tons, it handled roof truss sections weighing nearly 1,000 tons each, swinging them hundreds of feet overhead with a precision that would have been unthinkable for earlier generations of cranes. The VPC system kept the crane stable, automatically shifting its counterweight as the boom moved, ensuring that the ground pressure never spiked beyond safe limits, even as the load arced across the site. Operators describe the VPC as a kind of silent partner. As the controls are feathered, the counterweight glides along its path, always in the right place at the right moment. The system's automation doesn't just make the crane safer, it reduces the physical and mental strain on the crew. freeing them to focus on the lift itself rather than constant recalculations of balance and ground loading. But the same innovation that makes the 31,000 so adaptable also brings new considerations. The VPC's moving mass depends on a web of sensors, hydraulic actuators, and digital controls. In controlled conditions, these systems work in perfect harmony, but as the Texas summer heat rises or a job stretches late into the day, the mechanical choreography faces its own tests. For now, the VPC system represents the cutting edge of heavy lift logistics, shaving days off project schedules and rewriting what's possible on tight, busy sites. The true test, as always, comes when conditions are less than ideal. The Texas sun beat down on Globe Life Field as the Manitowoc 31,000 prepared for its heaviest lift yet. A 1,000-ton roof truss, nearly the length of a football field, hanging in the air above a half-built stadium. At ground level, the heat shimmered off steel beams and concrete, pushing the thermometer to 95 degrees by mid-morning. Inside the crane's control trailer, a 65-year-old foreman watched the hydraulic oil temperature inch past safe limits on the digital readout. The system was on the verge of tripping a shutdown. If the oil climbed much higher, the crane's fail-safes would lock out the controls, leaving the truss stranded mid-air. The crew gathered around, sweat streaking their faces, as the foreman barked orders that sounded more like advice from a bygone era than a modern construction site. "If we blow a line now, it's a waterfall on third base. Go slow. Stay cool." He called for a pause. The job clock ticked, but nobody argued. The stakes were too high. A single mistake would rain hydraulic fluid across the field, risking both the lift and the timeline. Improvisation took over where technology left off. The foreman's solution was simple and effective. Grab every available cooler and ice pack from the brake trailer, haul them up, and wrap them around the hydraulic tanks. Crew members raced to the nearby concession stands, returning with bags of ice meant for sodas and water bottles. Wet towels were draped over hoses, and portable fans were aimed at the overheated reservoirs. Someone even suggested hosing down the steel with cold water, a trick borrowed from refinery jobs in the Gulf. For an hour, the crew worked the problem the only way they knew how: by hand, by instinct, by memory. The foreman stood watch over the gauges, one eye on the truss still suspended overhead, the other on the temperature creeping back toward the safe zone. The oil cooled, degree by degree, until the warning light finally blinked off. The crew let out a cheer, part relief, part pride. The truss hadn't budged, the crane was back online, and the lift could continue. The foreman radioed up to the operator, voice steady. "You're clear. Let's finish it." The truss swung into place with only a slight delay, set down with millimeter precision atop the waiting columns. The job was back on track, and the story of the ice pack fix quickly spread through the site, earning the crew a round of applause at the next safety meeting. That day, the Manitowoc 31,000's advanced systems faced the limits of physics and weather, but it was the crew's quick thinking and a few bags of ice that kept the project moving. The lesson wasn't lost on anyone. Even the most sophisticated machines still rely on the hands and judgment of those who run them. For the men and women on that site, it was a reminder that ingenuity and experience are just as vital as any piece of high-tech equipment. Lamson's LTL 2600 Transilift wasn't built for empty lots or wide-open fields. It was designed for the tightest, most congested industrial sites in America. The heart of its engineering is modularity. Each section of the crane, from the boom to the counterweights, arrives on site as a separate component, ready to be assembled like a giant, heavy-duty construction set. The boom stretches up to 460 feet, but it can be shortened or extended in the field, matching the exact demands of the job. The real secret, though, lies beneath the boom: a pair of crawler tracks, each one adjustable between 24 and 37 meters apart, by widening or narrowing the stance. Crews can squeeze the LTL 2600 into tight corners or open it up for maximum stability on sprawling refinery plots. This flexibility means the crane can roll into place, even in the shadow of live process units, or under a web of overhead pipes, places where a fixed base crane simply wouldn't fit. Counterweight is handled with equal precision. The LTL 2600 carries up to 2,400 tons of modular ballast, stacked and arranged according to the lift plan. Each tray can be swapped out or shifted as site conditions change, adding weight for a heavy reactor vessel, or trimming back when space is at a premium. This on-the-fly adjustment allows the crane to adapt, hour by hour, to evolving project needs and safety requirements. In practice, this modular approach transforms what's possible on a live refinery or nuclear site. Instead of weeks spent pouring foundations or waiting for a single massive lift window, crews can reconfigure the crane overnight, responding to weather, ground conditions, or last-minute design changes. The Transilift's flexibility isn't just a convenience. It's a survival strategy in environments where every foot of ground is spoken for, and every lift carries consequences. In the refinery shadows, the Lamson LTL 2600 stood ready for one of the most dangerous lifts in American industry, a 950,000-pound regenerator vessel to be set directly over a live flare. The vessel's final weight had shifted overnight, forcing a pause. Digital readouts flagged a discrepancy, but it was the intuition of a 70-year-old rigger, a Lamson veteran since 1971, that pushed the crew to dig deeper. While computers measured load angles and cable tension, he walked the boom by flashlight, feeling for subtle heat in the rigging and listening for the faint tick of steel under stress, signs that sensors sometimes miss when the air itself ripples with heat. Manual checks began where the digital limits ended. The rigger and his team measured cable stretch by hand, recalibrated the boom's angle with magnetic levels, and double-checked every shackle and sling. They found a slight creeping elongation in the main hoist cable, the kind of slow shift that can turn catastrophic when a suspended load passes above an open flame. The decision was made to reroute the vessel's path, swinging wide to avoid the flare's hottest zone, even though it meant a more difficult set. Cal OSHA inspectors watched from the blast wall. The refinery's fire watch stood ready, hoses charged, as dawn broke and the lift began. The LTL 2600's crawlers inched forward, the boom arcing with deliberate slowness. Every movement was called out on the radio, the rigger's voice steady, guiding the team through the critical moments. The vessel cleared the flare by less than 30 feet, heat shimmering against the steel. At the final set, the rigger signaled all clear. A perfect placement, no incident. Later, the operation was cited in safety briefings as a model of human vigilance. For the Lamson crew, it was another day's work, proof that even the most advanced machines still depend on the hands and judgment of those who know their limits. The big AFRD's 4,000-ton capacity, the Manitowoc 31,000's VPC innovation, and the Lamson LTL 2600's modular strength have each set records in American heavy lifting, documented at sites like Vogtle Nuclear Plant, Globe Life Field, and the Chevron Richmond Refinery. Operator accounts and site logs confirm that decisive human judgment, such as halting a 3,740-ton nuclear module lift for wind or cooling overheated hydraulics with ice, remains crucial even as automation expands. While technical manuals detail capacities and safety protocols, some operational specifics, like proprietary software or incident reports, remain restricted and are not available for public review. Today, these cranes continue to shape American infrastructure, enabling larger, safer builds than ever before. Their legacy is visible in every skyline they've helped raise. As documented evidence shows, the future of heavy lifting relies as much on the experience of skilled crews as on the machines themselves.